So what I want to finish, I want to finish about the discussion of equations. So last time I introduced the idea of evaluating averages in the non-function steady state for the fact of any state of exponential duration with time, say minus q of a low occurrence at single zero with some degree of lambda. And the idea is that this goes by the exponential of the function f of lambda times t. This function is called the scale to generating function and satisfies just a very nice property. It's actually a very universal function. It does not require a lot of the information about the mathematical technology. Okay? Now, so I told you to just generate the equivalent, the scale equivalent of that quantity, d of t. So calculate average d of t to the n power connected. That will go like times some Tn and Tn on the L of the derivatives of this f of lambda, df, d lambda, dn f lambda, at lambda. So, the f lambda generates the scale equivalent, the scale t. That t there is the ballistic scaling. So, in general, we did not go to the theory. You may have different powers, there are different powers, square root of t or whatever. But in the case of the current ballistic sequence that has been field theory, in this first power of t, then I calculated explicitly this that f of lambda in CFT for energy transfer. So I just calculated it by putting here T minus T bar and evaluating the average using free energy type of idea. In the end, it was just a difference of free energy. And then this is formula to tell the f of lambda is C pi over 12, characterizing the CFT. And then there was beta f minus lambda, 1 over beta f minus lambda, minus 1 over beta f, plus 1 over beta right, plus lambda, minus 1 over beta right. Just actually difference of free energy with shifted inverse. The insertion of that exponential lambda of the current shifts the inverse temperature. The same for the we have here free energy. That's an important concept. But with beta left shifts to beta left minus lambda and beta right shifts to beta right. So with shifting of inverse energy, you just have to calculate free energy to different in the temperature. So we get that. In fact, we get a difference in the free energy because at lambda equals 0, the whole thing should be 1. If lambda equals 0 here, then we have the 1, the whole thing, so the whole thing is 0. Indeed, I put lambda equals 0, and this is so the difference there is just the rest is 3. So this is a calculation in CFT, and this is a nice assembly point of assembly time of the following transfer of energy from left to right. I could put that at equilibrium where I would have beta equal to beta right, and that would but out of equilibrium.
It's better there, but one could still hear a little bit. Okay. Okay. That's fine. Okay. Now, so what I want to do today, 2 things, well, or maybe 3, or whatever time there is discuss the fluctuation relation, and that kind of tells us is something quite fundamental, quite general, and it's something that says that within this function, this f of lambda, defined in that way, there is encoded within it information about the non-equilibrium steady states, and it's purely out of equilibrium. It's something about non-equilibrium, about forces, on the left, on the right, so some forces making the energy move around. Okay, fluctuation relations, and the other thing is about a generalization of this result, of the CFT result, and again, it looks like a very strong statement, but this is what it is, to arbitrary many-body system. So arbitrary many-body system, that looks pretty strong. Well, maybe short-range interaction, blah, blah, something like that. Okay, and indeed, it is possible to generalize this idea of free energy shifted by, with temperature shifted to arbitrary many-body systems, as long as you know appropriate, you have appropriate information about these systems. And the information that you need for these systems is its Euler hydrodynamics. So here, I mean, it's just thermodynamics, but in fact, we had free energy of the left movers and free energy of the right movers separately. So that's the end that allows you to study currents. So it's really like the Euler hydro. So in fact, what I want to say is that with Euler hydrodynamics, that can be generalized, and the generalization is a bit less trivial than that, but still, so something similar to that happens. And then you can write some equation or some formula for f of lambda in complete generality, and then you can see interesting things such as phase transitions and things like that, dynamical phase transitions. Okay, that's the idea. Okay, and then maybe at the time I talk about the relation between this and twist fields, but I'm not sure if I get there. Maybe I get there. See, or I have to give 2 other lectures, but no, maybe not. Thank you. Okay, so yes. Okay, fluctuation relation. So this is just make sure that I get it right. Yeah. So this is a relation that we can observe already explicitly at this level. So we see the following relation. If I look at f of lambda, the function, well, this is the same as f of some inverted lambda, right? Beta left minus beta right minus lambda. Put that in here. I see that I get exactly the same term. Right? So beta left minus beta right minus lambda. That becomes this, and this becomes that. Relatively simple. Okay, so this is a fluctuation relation. What it means, so this general fluctuation relation, so let's say A, B, C, A fluctuation relation is that relation there. Okay? So what it means is that the probability of if you try to recast if you try to remember the relation between the scale cumulant generating function and the exponential form of the probability, right? There was a probability for a current, which was like exponential minus t times some large deviation function, which looks a bit like an entropy. Okay, so what this relation means, if you do the map between that, what it means is that the probability, the ratio of probability for a certain current over a probability for the negative of the current is, well, if the current is positive, say, this ratio is very large. So it's much more likely for the current to go from left to right if your temperature on the left is bigger than the pressure on the right. Okay, so that should be larger than that, but it's not infinite, but it's very large. And it says that this goes like an exponential of, I guess, would be beta right minus beta left times the current. The ratio takes a simple form. That's the meaning of that in terms of probabilities. So this is if t left greater than t right, then and j positive, then j positive has more probability than negative. Okay, that's what it means essentially. Okay, so there's this simple relation, and it says that these kind of external forces tell you about the probabilities for current going in one direction with respect to current going in the other direction. So that's kind of the meaning of that. Now, this is supposed to be a very general relation. There's very general arguments for this relation. And there are ways of proving it, or kind of at least giving some arguments for it. But we can see it here directly at the level of the CFT. Okay? Now, I would like to give kind of some arguments for why this relation should be true in general, not just in CFT. Okay? In fact, one of the things when we derived that, it was interesting because we could explicitly observe that relation, although it had been proven for particle systems, maybe for simple classical system. For CFT or quantum field theory, it was not obvious at all that this should be true. And so we could observe that it is true. But it seems like something even more general. Okay? So questions about this fluctuation relation. So this is the first thing. So you see that if you know that function f of lambda, and you see that it has satisfied a symmetry relation like that, and it tells you about what was driving the non-equilibrium steady state, right? So there's a state there, it has a temperature, in fact, it has two temperatures, it has a difference of inverse temperatures. And you see that this is what was driving it. And if this difference is 0, then f of lambda is symmetric. So yeah, sure, the current, all the odd cumulants are 0 is symmetric. That doesn't tell you a lot. Maybe it tells you it's at equilibrium. Okay. But if it's not 0, it tells you a bit more. There's another symmetry with respect to another point. Okay, so that's the interesting stuff. Okay. How do you show that? Well, the standard proof of that come from using time reversal variance. So this is supposed to be valid in models that have time reversal invariance. If the model does not have time reversal invariance, like the Hamiltonian, fundamental Hamiltonian dynamic is not time reversal invariant, then this is broken. That's what people expect. Okay? So time reversal invariance is important for the fundamental dynamics. Of course, the state itself is not time reversal invariant, the non-equilibrium steady state, and that lack of is not, but then it transforms in a certain way, and this is what tells you how it transforms with the time reversal invariance, right? That's kind of the idea. Okay. So how do you do that? Well, so there are different ways, but one way that we came up with is to use, so in generic many-body quantum system, to use some kind of a scattering formalism. So we use the idea that the non-equilibrium steady state, rho sat, okay, is essentially a limit when t goes to infinity of the evolution in time of the initial density matrix, which was exponential minus beta left, h left, minus beta right, h right. And these two, they commute with each other. Right? So this kind of rho left times rho right, okay, is ITH. Right? So this is the non-equilibrium steady state. Of course, this formula is not very accurate because the limit doesn't exist in the sense of matrices and all that, but we mean this formula in the sense of evaluating local observables, right, in the usual way. Okay. Now, what you can do is that you define your scattering matrix S plus as limit when t goes to infinity of e to the minus ITH e to the ITH0. So what you mean by that is you say, okay, now let me define this as evolving first backward in time. If I see that as applying on the density matrix, first backward in time with the known, the trivial Hamiltonian, which is just the direct sum of h left plus h right, without the delta h, right? So just the one where the two are separated, right? So this kind of doesn't do anything on the initial density matrix, right? And then evolving forward in time with a true Hamiltonian. Okay. Now the point is that because you have an extensive Hamiltonian there and an extensive Hamiltonian there, and the difference between these two things is just a little delta h, okay, that makes sense as a limit. So this has a good limit in an appropriate sense. I'm not going to do any mathematics here, but so just that doesn't make sense, just that, but the limit of the sum operator and the inverse operator, where the difference is just a e to the small delta h, e to the small thing, that makes sense. Okay, so you can think of that as a limit, as an appropriate operator, acting on appropriate space. Okay. So rho stationary then is just s plus rho initial, rho 0, s minus. Okay. You can also think then as evaluating operator in the stationary state. Okay, and then you just have to insert this. Sorry, this was s plus inverse, right? Yeah, that's what I want. Which is the Hermitian conjugate, all that. Yeah. Okay, s plus inverse. So you can also think about applying, this in that definition of the stationary state for local observables. What you get is s plus inverse operator, s plus in the initial state. So you get you see that in order to evaluate things in the stationary state, what you have to do is just transform your observable with the scattering operator. Okay. So the scattering operator is you can see it as a map, observables to observables, that allow you to evaluate things in the stationary state. Okay. So that's one thing. Then you can actually work it out explicitly. It is in CFT, that's interesting to work it out. When you do S plus on T of X, for instance, what do you get? So let's do S plus minus on T of X, S plus, exactly like what we do here, right? Just evolving this local operator. So it's not complicated. What it means is that you first evolve in time. So this is limit T goes to infinity. I evolve in time now first with the true Hamiltonian is inverse here. So is that one that acts first, right? So I get then e to the minus I T H0. Then T evolve in time with the true Hamiltonian is I T H0, the full Hamiltonian, where T just evolves, straightforwardly. And then I evolve backward in time with the Hamiltonian where the delta H is being taken away. And now there's a boundary condition. T equals T bar, there's reflecting condition. So I can do this calculation explicitly. The boundary condition transforms T to T bar. Okay? So if X is large enough, so this is certainly negative, right? So that will evolve in the opposite direction. So if X is negative enough, then nothing special happens. You get back to your T of X. Nothing different. Okay? But if X is positive, then something special happens because as you get back, you will cross the point 0. So somehow here you evolve in time. You start at that point, say, so X is negative. You evolve first forward in time, and then you try to evolve back, and then you evolve back with a different color. You evolve back, but then you reflect. So if X is negative, you have to use the reflection. So that's going to be T bar of minus X for X. This is greater than 0. This is the opposite of this picture. So if X smaller than 0, because you evolve, it's the opposite picture. You evolve like that, and then you try to go back when X greater than 0, and then you have to be there. So in the end, you always end up on the left-hand side, okay, which is fine. So which is kind of the right thing, and that tells you then is so very simple. That means that in the stationary state, T, the right mover, only sees the state on the left. And that's what we had previously, right? The right movers were thermalized by beta left. So it's the same thing again, right? But just with a scattering point of view, right? So it's the same thing again. And similarly, you have S plus inverse of T bar of X. S plus is going to be either, now it's going to be just on the right. So T of T bar of X if X greater than 0, and T of minus X if X is smaller than 0. And now that just ends up on the right and sees only the right temperature. So it's a kind of a simple way of seeing the stationary state using this more formal thing about the scattering matrix. Okay. Now this S plus has a few properties. In particular, it intertwines the full Hamiltonian with the disconnected Hamiltonian. It's called intertwining. And that's actually a consequence of these calculations that I've just shown. In a sense, one can show that by doing this similar calculation on the Hamiltonian H0 and H. Yeah, good question. Sorry. So this is general. I haven't proven it in general, obviously, but this is expected to be a general property. One of the main property of this S matrix studied in general quantum many-body system. Okay, intertwining property. So CFT is just an example of that. Yeah, but it's supposed to be general. Okay, and so okay, yes. Now we want to use that in order to derive this equation, okay, from that. So, and the way that we do is like that. So we say, okay, because I have 2 page 9. Okay, this now. So we say the following. So we assume now, we have that now that we assume that there exists a time reversal symmetry, and we call it tau. Okay, tau, such that the Hamiltonian is invariant under this time reversal symmetry, and tau is an antilinear. I mean, the anti will not play too much of a role here, but you see if it's preserved the Hamiltonian is antilinear, then it changes time to minus time. Okay, and also that independently the left and the right Hamiltonians are also time reversal invariant. You see, they are not space reversal invariant. They are just on the half line, but they can be time reversal invariant. and we assume that is the case. Okay, it's true in the CFT, for instance. Okay, but then we assume this in general. And so we assume that there is this, and we're going to use this in order to derive this relation. Now, of course, as we think about time reversal symmetry, we should also think about the other scattering matrix, the scattering matrix that, so by the way, this is a bit like this adiabatic way of turning on an interaction, right? Where you start from far in time and slowly turn on the interaction to get your true Hamiltonian. It's a bit like that, except here you express it as you don't slowly do it, you do it just at very large time, and you just do a small change, local change. So you don't need to do it slowly. That's the idea, because it's just a local change at delta H, so that's fine. So here you go backward in time and with like in the true Hamiltonian, and forward with the interaction that builds back the right thing. Okay, but you could do the whole thing. You could go forward in time and backward, obviously, and then that's the same by this because time reversal. So you can construct S minus, which is the limit t goes to infinity, say, of just the opposite. So e to the minus I, sorry, S minus is going to be, so it should be just the right thing, minus I th. Well, it's t goes to minus infinity, well, or t to I th, e to the minus I t h0. So this is not S plus inverse or anything. It's a different thing, right? The h is still there and the h0 is there. It's just the opposite time thing. Okay. And okay, so we have that, and now we notice again that same thing, right? S minus h0 also intertwined with h. So it's the same thing for h, but now we can define, say, h left and right plus as being h plus h left right, s plus minus, but and then h left and right minus is something different, right? The left and right Hamiltonian, if I apply the scattering, S plus or S minus scattering matrix, they are different. If I apply on the full Hamilton on H0 Hamiltonian, then I get the same. So S minus H0, S minus is H, and the same thing for S plus. So it's different from the left for the left and right, but it's the same for H0 itself. Okay. Okay, so this is kind of the structure we have, right? It's like scattering matrix with the plus and minus and left and right here. And then it's just really a matter of using the structure and some algebraic manipulation using the structure to get to the general fluctuation relation. Okay. So let me just show you the steps there, which make everything work. So we want to calculate that. So we write it like that. So the integration minus t over 2 of the current, we write it as the difference of something I called delta H. In fact, in my last lecture, at t over 2 minus delta H at minus t over 2, where this delta H is really H right minus H left over 2. So it's the difference at two different times of the difference of the energy on the right and left. Have the difference of the energy on the right and left. So you can calculate that, of course, by the conservation laws. That and that is the same thing. So it's just total energy transfer from left to right, essentially. Okay. And then we write this thing that we want to calculate. So is the t f of lambda, the thing we want to calculate is what is the average of that exponential. And now, instead of putting exponential of the difference, I'm going to put a product of exponential. So lambda delta h of t over 2, and then exponential minus lambda delta h of minus t over 2 in the stationary state. I'm separating this exponential. Now, this is kind of a wrong thing to do in quantum mechanics because the delta h at two different times don't commute. Okay? So there is t over 2 here and minus t over 2. This and that don't commute. So this is not the same thing as the exponential of the difference, which is what I should really write. Okay. But I told you also last time that in fact that formulation is not quite the right one, because actually what you should do is to do like maybe two-time measurement. Do a measurement first, let evolve the system, do a measurement again, and then that projection is more complicated and all that. And for this purpose, this is actually slightly better formulation, in fact, in quantum mechanics from that point of view. In any case, it is expected that it doesn't change too much between this and this, but okay, certainly CFT, it doesn't change at all. In general, it's more difficult to argue that it doesn't change at all, but in any case. So let me start with that as kind of the correct formulation, let's say, okay? So yeah, so any questions until there, right? Large division function that I would like to evaluate. Okay, so then it's just a matter of putting things together, right? So this is, okay, I do large time limit here. So large time, I can use my S plus and S minus now that, so this is the average of exponential lambda, and now I have delta H minus, because the minus has the e to the I th there. So the e to the minus I th0 does not affect H right minus H left, because H0 is just H right plus H left. It commutes with it. Okay? And e to the I th is the right evolution of a local observable. So this is really an S minus that goes there. And here is exponential minus lambda delta H plus. Okay, delta H plus. So you just kind of reinterpret your large time limit in terms of application of the scattering operator. Right? And that is valid from the point of view of local observables. And in the end, this is valid for the point of view. In fact, I should write in the sense of the leading large time limit for that object. So one has to argue properly for that, but leading large time limit. Okay. So this is just using that formalism. I rewrite this as H minus H plus. Okay. Yeah. So to be precise, you know, there is a I should write a log of that. I should do 1/t and things like that. In fact, to be precise, the proper derivation is a bit more than that. This is kind of the trivial simple derivation, but it's sufficient for our purposes. You know, you don't see the t anymore. In fact, this I should take log of that and kind of 1/t. I mean, the log of that is something that grows linearly. Okay? But for now, I think this is sufficient, and we see the fluctuation relation coming out. Okay. Okay. So for now, I say it's something like that from the point of view of the large scaling in time. Okay. And then I write this. So it's extremely simple. Okay. That's why I do it like that. I write this as trace, and then I have my non-equilibrium stationary state, which is written like that, right? So I have written like that. So rho stat is this, right? So this is exponential minus, so there's beta left, H left, plus minus beta right, H right, plus. That's my stationary state, essentially. Yes. Okay. There's a thing there. So I write this there. In fact, let me kind of work it out there a little bit. So this is exponential of minus. I can put these two things together, H left plus H right plus, into a single Hamiltonian. So H. So I have beta left plus beta right over 2 times H. And then I have, put thing correctly, plus beta left plus beta right. Then I have delta H plus. Okay, I write it like that. So that's my stationary state density matrix. It's with the plus like that. Okay. So there's one bit which is the H left plus H right plus, which is just the full Hamiltonian. So this is H left plus H right plus, the same as minus. Okay. And the other thing, which is H left plus minus H right plus delta H plus, and this has a difference, beta left minus beta right. Right. Okay. So I put that in here, and now I have all the ingredients that I need. So there's minus beta left plus beta right over 2. There's the delta H plus, so there's then exponential beta left minus beta right delta H plus, and then there's the other thing there. So exponential lambda delta H minus and exponential minus lambda delta H plus. And all this in the stationary state, and I put the 1/z there that will not, is just the normalization of the stationary state that will not affect the calculation. Okay. So trace of all that. So this is the expression now in terms of these H plus, H minus, and all this. And then, then what I want to do, have that is I just simply want to apply the time reversal symmetry. So, yeah, that's right. Yeah. So first of all, these delta H, so this delta H plus, I can bring it the other side. So this delta H plus commutes with that H, because that's just an H plus H minus, it commutes. So this I can bring it to the other side. I observe that I have now, so if I take this away, here I'm gonna have instead, I actually want, I'm gonna have beta left minus beta right minus lambda of delta H plus. Okay. So just rewrite it that way, okay? And then if I do what I do, then I apply time reversal symmetry on this whole thing. The trace stays the same and all that. What happens is that the pluses become minuses. So that becomes a minus, that becomes a plus, that stays the same, okay? And I can bring it back, then it's here. I can bring it back, now I change color, the blue, okay? So this whole exponential now, I can bring it back there. And what I observe is that I get the same expression as I had before doing this blue transformation. Before doing this blue transformation, the same expression, except that this difference is beta left minus beta right minus lambda. Instead of being there, it's there. And here there's a lambda. So these two things have been inverted. Okay. So it's a bit quick, right? But using cyclicity of the trace and the fact that these delta H plus and minus commute with Hamiltonian, you get to inverse them. Okay? So you apply time reversal symmetry, pluses become minus, you invert the thing, you see that you've obtained this exchange of lambda goes to beta left minus beta right minus lambda. So this is the one way of proving it. At least you see the structure. It's not a complete proof. If you want a more precise proof, the way that it works is that it's a bit like I was doing last time, maybe I'm going to do just now, is that you take a derivative with respect to lambda to bring down the current, and then you have an average of a local observables. Then you work at the level of local observables. It's the same steps, however, but you work at level local observables, everything's well defined, you have the T explicit, everything's fine, and then you get back to the F of lambda. Okay? But that's the structure. This is what actually happens. You do time reversal symmetry, exchange plus and minus, and this exchange of plus and minus allows you to, well, you see that it becomes a lambda goes to beta left minus beta right minus lambda. It's purely structural, right? It's kind of algebraically it's very simple, right? Then the rest is just the detail of how it works, why it works, and all that. So that's one way of looking at that using this scattering operator formalism, which is kind of relatively interesting and makes the thing quite simple. Okay. So this is then supposedly a very general relation, right? So it's supposedly something that tells you about the fundamental, the fact that your stationary state is a scattering evolution of a tensor product of two different density matrices, right? With different temperature. That's what it encodes. So you calculate your F of lambda, you don't know where it comes from and all that. You see the symmetry point, you say, well, this is out of equilibrium with this difference of inverse temperatures. It's going to encode that. So that, in fact, in particular, that means that there's a lot of relations between the cumulants, right? These Cn there, as functions of the temperatures, right? They satisfy quite a few relations. You expand this and that in powers of lambda, it's relation between cumulants, right? So it's non-trivial relation between the cumulants from the fact that it's a stationary state. Okay. So this is quite an interesting relation. Actually, a lot of people have worked on that. It's generated a lot of articles, and it's kind of one of the fundamental thing that kind of replace standard fluctuation relation at equilibrium, so to speak. Okay. And people say, anyway. Yeah, questions about this? Okay, so the other thing, that's one thing that I wanted to say, kind of to go over. So okay, there's this general fluctuation relation. Now that can be seen in CFT. So there's two things, right? This can be seen in CFT. It is general, and the other thing is, well, there's CFT, the result is very simple, so shifted inverse temperatures. Well, this is also something relatively general. So you can also make a general argument to say, what is f of lambda? It's not just shifted temperature, but it's kind of modified temperature in some way, which is in general more complicated, but still in some way that you can evaluate. Okay. So that was my second point, B, and let me then go over that. No, yeah, sorry, I should have been more clear. So yeah, and actually, even you asked me to produce some list of references, which I showed. I'll try to do that soon. But yeah, indeed, this was known actually. It's related to this something called Jarzynski relation. I think these were called Jarzynski relation. So there's various relations that have been studied since I think it's since the 90s, probably, or 2000, something like that. In other contexts, in context of stochastic models, for instance, people have obtained relations like that. Then in free Fermion models, people have seen things like this. Of course, you can calculate explicitly. In particles, interacting particle systems, there was kind of idea that it should be there. Now, so this was really, I mean, relatively well known as a relation. And in this work with Denis Bernals, what we wanted is, can we prove that in GFT in some way, right? Because it had not really been addressed in GFT. And the idea was to use the scattering formalism, which is relatively, not well understood in many body system and QFT. So it is there, it exists. And then you have a proof, which is, it's a bit formal, but it makes it relatively clear where it may come from in QFT or even many body systems. There's also, here I take the large time limit, even there's a similar relation for finite time. So that should hold, again, under certain assumptions and all that. And here we were looking at that directly in the infinite time limit for the stationary state. So, yeah. Sorry? Yes, indeed, yes. So if beta right, yes, they're equal, yeah. Which is, exactly, completely straightforward, yes. Mm-hmm. Yes, exactly, yeah. So these f of lambda, typically they are convex function. One can argue that they must be convex. This like the positivity of the matrix of susceptibility, that's what it says, that f of lambda is convex. So in general, one can argue it's convex. And so there's a symmetry. And here what you're saying is that out of equilibrium, the symmetry point is generically shifted. So this is my 0. And that would be the symmetry point, say, I guess, beta left minus beta right over 2 or something like that, right? And that's a characteristic of having the symmetry of a non-equilibrium steady state. I don't know. Yeah, I don't know. Maybe somebody else. I don't know. Yeah. I'm not sure. Yeah, if it's related to that. Yeah, I'm not sure. Yeah, I don't know. Yeah. So there is this symmetry, and and sometimes if you do numerics, sometimes you can do numerical calculations to calculate this from that in some model. This and it's non-trivial to recover that symmetry. Actually, a priori, you can calculate f of lambda in some ways. Complicated stuff. It's actually not easy to calculate these large scale cumulants because you have to have really good statistics. And when you have the right thing, you see there's a symmetry there, and that's so in some of the works we did, where we had some explicit formula for f of lambda, and the formula is not obvious at all that there is a symmetry. It's just some complicated thing with Bethe and Zas nowadays. You do numerics, you put that in, it's yes, actually there is a symmetry at the right point. So probably it was the right formula, but it's kind of not obvious. So this is a very interesting question indeed. So it's kind of what I guess I'm going to do a little bit here. So what you're saying is that, well, if I shift lambda like that, okay, and I put it at the right point there, then it becomes symmetric. So it looks like it will be equilibrium. So it looks like inserting a total current integral, I would just change the equilibrium state, right? So, and indeed, it is kind of the case. So, and that's also something people have studied in the context of a stochastic system where you say there is not equilibrium, it's stochastic, not that, but you want to insert a total current integral, and then you realize it's the same thing as changing your stochastic process a little bit. So you just have a new stochastic process that depends on lambda, and that kind of knows about the current. And then maybe in some here in this case, for instance, well, with the right choice of lambda, you would recover something that looks like equilibrium. So if you start out of equilibrium, something like that, yes. So there is this relation. So the insert is observable. It looks here like maybe you could change the state, and that would be the equivalent of inserting that observable, and then that state would now have that symmetry for that observable, right? Yes. Basically, so you exactly. So here you have a stationary state with current, and somehow you insert the current weight just to counteract that current that you already have in the stationary state, to counteract it, and then it becomes zero current. So inserting this exponential of J is like changing the weight of your measure, right? Because your measure is exponential minus beta h, but then you change the weight beta h plus lambda and integration of J. This new weight, right? So the initial measure has a current, but with that new weight, with the right lambda, it has no current anymore. So okay, and this is a very important observation, which is the observation fact that leads to the general formula for the f of lambda. Okay, and the observation indeed is exactly what we just discussed now, is that if I were to calculate, insert this minus t over 2 to t over 2 integral of the current, okay, and then I put some observable there and divide by the same thing. So here, you see, I just modified the weight of my measure, right? I changed. So this is a trace with exponential minus beta h, but then beta h and that. Here, beta h and that. So I really modified the measure, both numerator and denominator, with the right normalization. And I call that O sub lambda, right? New measure, okay? O sub lambda. So this is a good measure. In particular, 1 sub lambda is equal to 1, and it's positive because this is a real thing that I've inserted there. It has it has nice property. I mean, one cannot show all the property, but supposedly it is also clustering. I put an interrogation mark, so maybe like O of x, O of 0 goes to 0 as x goes to infinity. I don't exactly know how to prove that, but since the current is local, maybe it's the case. I don't know. Okay, so we don't know, maybe, but it is a measure. And in fact, right, so it's measure. More than that, this is the interesting observation. We were saying, you insert the current and that kind of counteracts the current that steady state already has. But is this measure, is this thing a steady state or not, right? Well, I integrate over all times here, right? So if I shift the time here a little bit, right? If I calculate O of S, well, that's the same thing as O of 0. Because if I put an S there, or an S prime or something, O S prime, let's say. If I put O of S prime here, this whole average is, of course, stationary, so I can shift times everywhere. By S prime, I have S minus S prime. And now I take the large time limit. Maybe I should say, yeah, here. T goes to infinity, I take the large time limit, so I could shift S prime, doesn't matter. So that should be, as long as the boundaries don't influence anything, right? Of course, as long as there's no boundary effect. So as long as there's enough clustering in time. Actually, it is non-trivial, clustering in time. But okay, we'll come back to that. We discussed a bit that with William's question in previous lecture. But so if the large time boundaries don't affect anything, yes, it is indeed the time translation invariant. So it's stationary. So this is a stationary, positive clustering, whatever measure. More than that, it is also homogeneous, and that's actually a bit. So this is 0, S, x, 0. It's homogeneous. I can shift in space and get the same thing. Why? So here, the current is inserted at 0 only. Why is it that if I shift in space, I still get the same? This is a conserved current. So maybe I can use the continuity equation. So what I say is the continuity equation. I say, well, okay, so suppose I shift in space. I can shift my whole current by inserting at infinity some small segments of integration of the density. So I have integration of the current there at 0. Okay. This is the same as integration of the current but as long as I add that plus, yes, that and that. Some integration of the densities at between 0 and minus x at minus infinite time. Okay? So in other words, what I'm saying is that the integration, well, I'm using dtq plus dxj equals 0 in the integral form. So in other words, integration over contour dx mu epsilon mu j nu is 0, right? The integration of the perpendicular current along the contour is 0, just coming from the local form of the continuity equation. So if you integrate, I think I did something like that in one of those lectures. You integrate that over a whole square, and then here you have in time the boundary terms of the time integral, and here in space the boundary term of the space integral. So you get an integration around the square, Stokes theorem. And so the current at x equals 0 from minus infinity to infinity is the same as the integration of the current at minus x plus the integration of the densities at minus and plus infinite time. So okay, so that means that if I calculate this, I have this exponential lambda integration of minus infinity to infinity of the current with O at x. This is the same thing as exponential lambda integration minus infinity of the current now at minus x. Now I add some little things, so integration dy from 0 to x of the densities at y in infinite time minus the density at y and minus infinite time. Okay, plus or minus, I'm not sure which sign I should put. Okay, and then times O at 0. So I shift everything to minus x. No, sorry. No. I shift everything to minus x. Sorry, shift everything. So this is O0, and now I shift back. That's the whole point, right? Integration from minus infinity to infinity j0s, and then I add integration from 0 to minus x dy of the densities ys minus y minus s. It's plus or minus, I don't know. That's in the exponential. And then I have times O at 0. Yeah, so, I write that, I use translation invariant, shift the current, and I reshift the current back to 0 by adding these extra integration of plus and minus infinite time. And then if I believe again that there is no correlation between the thing that plus and minus infinite time, and this goes to 0, and I'm left with the same thing as I was. So there's translation invariance. So by the fact that you integrate a conserved current, you have translation invariance. You have both time and space translation invariance. And that means that you have a nice homogeneous, I keep that again, homogeneous stationary clustering, we hope, state. And what are these homogeneous stationary clustering states? What can it be? Then there's this general, I think there's something called the Ergodic Principle, which says that any state which is homogeneous stationary clustering must be a Gibbs form type of state. Quite non-trivial maybe, but anyway, so that means O lambda must be O of some beta of lambda, some vectors of betas there, all the constant quantities involved. Okay, this is highly non-trivial, right? Why is it the case? I don't know of any proof of that, but that's a principle that you can use. And of course, these principles can only work if you put here all the extensive conserved quantities. So it's the same problem as what I was talking about yesterday. You have to know the space of extensive conserved quantities, and you have to put them out there. Otherwise, you're missing something, right? But it says there should exist some betas such that this is equal to that. And that's your point. Your point that yes, this state I can choose lambda so that now it looks like it's equilibrium. So it will look like a Gibbs state with different betas, and you have to find what the betas are. So I'm not sure what you mean. Why I do that, or so yeah. So why I do that, I haven't explained yet. Actually, why I consider that measure what it gives me. I just do it now. Okay. But if you just believe me, I consider this. Then you're happy. Okay. Okay. Fine. Yeah. So okay, but that good. So that's the next step then. Okay. This is just yeah. Why not? But it's not quite what we want to calculate. We want to calculate this. But that looks like a free energy for this measure. Let's see. That's a bit the intuition. Let's say. Right. So this is a measure. What you want is the denominator. That's what you want to calculate. So it's a free energy for the measure. You were saying F is a free energy. So in that sense, yes. Okay. But I mean, not exactly. So the precise way then of doing it is to say, okay, if I do derivative with respect to lambda, so d lambda of f of lambda. And this way is the right way of doing like the CFT proof of the fluctuation relation that I was showing. Actually, correctly, that's what I would have had to do. So take derivative and then work with the result. Okay. If you do that, that's the derivatives to lambda. There's 1 over t. There's a log, and there is this exponential lambda integration minus t over 2, the current s at s. Okay, so that thing, okay, that I want to evaluate. Now I do the derivatives is 1 over t, evaluated, of course, at t goes to infinity. Okay. I do the derivative, so I bring down the integration of the current J0s, bring this down. I still have the exponential, and I divide by the average of the exponential because it's a log. So this is exactly the average in that lambda measure. Okay, so that's why I want to consider it. Okay. So the F derivative is the average of the current in that measure. So it's like a free energy, right? When you differentiate a free energy, you get the average densities. So differentiate with respect to the inverse temperature, you get the average energy. Or to the chemical potential is the average density of particles and things like that. So this basic relation is the same thing here, except now is the current. Okay, now I have an integral of the current. This is not quite the lambda, it's lambda comma t. You know, it's like this one, but taking t finite, right? It's not quite. But then if you make the assumption that again that the boundary terms don't matter too much, and that what matters most is the bulk of that integral, that it does not, that correlation with boundaries decay exponentially, then that will scale like t times something, which is time. I mean, the measure is an invariant of the time translation. So it's t times something. That's times a unique thing. So the t's cancel out. It's nice. And then we have j 0, 0 in that state. So this is the main relation. That is the main relation. So that's why you want to know what this measure is. And now I say, okay, well, there is a beta of lambda. So this is the average. So now it comes back to a bit to what I was saying, at least one bit of it. If you know how the Gibbs states, and you know it's Euler hydro, that means that you know how to evaluate the currents. The Euler hydro is the densities and currents. If you know how to evaluate the currents, then you know the derivative of f of lambda. You just don't know yet what this beta of lambda is. Okay? CFT is that. It's just a simple shifted betas. So that's an explicit implementation of this stuff in CFT. But in general, what is it, right? So that's the next step. So does that clarify? Okay. So then for the next step, we need to use hydrodynamic ideas. And then we get the answer, the full answer, which is quite nice. So what are the hydro ideas? So we need to use the hydro projection idea that I talked about yesterday in my seminar. So yesterday I said, you know, we can write 2-point functions by projecting over density. There was this hammer picture. No, that. Okay. So what is this? If I write, so the first thing, let me get a result that would be useful then. Okay. And or maybe I just, okay, no, let me just calculate that. Okay, indeed. So let me just, before I do the hydro, this is the state I want to calculate. So let me calculate the average of some density in that beta of lambda. Now I know that the average densities, they fix completely the betas. It's just, right? So if I know, so the QIs and the beta i's, there's a bijection. If I know all the QI's, I know all the beta i's. If you know all the average, you know the average energy, number of particles, and momentum, well, you know the chemical potential, temperature, and boost. Well, so I just want to characterize the state by calculating the average QI's densities. Okay? And I'm going to do a derivative with respect to lambda of that. I do the respect to lambda because this is where I get information about the state nowadays, right? Now, this is the derivative with respect to lambda of beta, which is specific. I don't know what beta is yet, okay? J, let's say, times d beta j of qi. I put it at 0, 0. I'm not going to write the point where it is now. Now, this is the C matrix, right? This is d beta j d lambda times the so-called C matrix Cij, the matrix of susceptibilities. And so this is average, actually with a minus sign. The C matrix is the average of Q, J, Qi. When I differentiate with respect to the betas, I bring down the total charge, connected correlation function. Is susceptibilities. Okay. So that's that. Okay, fine. But I still don't know what is this d beta j. But I know that this is dd lambda of qi in the lambda state, right? Because I have that equality in the lambda state. That lambda state that I wrote, I guess, that I erased. Okay, that lambda state with the exponential of the current. So that I can evaluate explicitly because I know. So this is integration from minus infinity to infinity of the current. It's the current. It's some current with some index, right? I mean, into the lambda j, I didn't say what current is it, but it's one of them within all the available current. Let me call it I star. It's some specific current, okay? So fixed index. Or maybe it's the current 0. Let's say doesn't matter. It's one of the fixed indices. Okay, J0. So this at 0t, and then I have qi lambda. So the indices are completely arbitrary. I didn't tell you what is what, okay? And for instance, the energy current is the 0th one in QFT, in CFT, in my notation, okay? So that's what it is. And since I differentiate both the numerator and the denominator in that, then I get the connected correlation function. So what I have to evaluate now is this connected correlation function, right? So we're kind of almost there, right? So if I know the connected correlation function, I do this equals that. And I have a flow equation for the betas. D beta dynamic equals that. So I just have to solve a differential equation. That's the idea, right? So the last bit missing to evaluate is the integration of a current density connected correlation function integration in time. Now, how do we do that? This is difficult. It's correlation function. But yesterday I told you we can evaluate correlation function by using projection. So let us do that. And it turns out, I mean, this is, again, the derivation is not rigorous at all, but one can make the derivation actually quite rigorous and with all the terms now that. But basically what you say is that you rewrite this in terms of projections, and using projection, you can have quite an explicit form for this 2-point function, which is supposedly valid at large space-time. And so in principle, then valid under integration over large time. Okay, that's the idea. So I guess the conjecture is that large time integral is a hydrodynamic type of object. But again, one can make that more precise and actually by using Fourier transform and all that, and then it's kind of clear that this is the case. Okay, for now, this is sufficient. So what you say then is the following. We want to evaluate that. Okay. Now let us recall what we had. So according to linearized Euler hydrodynamics, if I calculate, if I look at the 2-point function of conserved densities, that satisfies a certainly. So that satisfies a nice linear equation. So this evaluated in some state. It's a nice linear equation obtained from projection and all that, and what it can be written like that with this flux Jacobian. The linearization of the Euler equation. the derivative of the average kth current divided by the average Lth densities in the state. Okay, so this is the linear version of the Euler equation. It's kind of linearized Euler hydrodynamics, and that, you know, written in the appropriate form is proven rigorously and all that stuff. And so that's a nice equation. In fact, that means that it can be solved explicitly. All right, it's a linear equation with constant coefficient because this is with respect to a fixed state. Right? It's just 2-point function, right? So people have written this kind of solution, hydrodynamic solution, and here I'm writing it in real space-time. It's it's a simple linear evolution of t proportional to x. So you can write it as delta function of x times identity minus matrix AT times KL, say, times the C matrix CLI. Right? So the 2-point function can be written explicitly as a matrix delta function. So delta function of matrices, which means that you diagonalize the matrix and then you put delta function of the eigenvalues. Okay, that's the usual thing of function of matrices. Okay, and you can see that this solves that. It's immediate to see that this solves that. And that has the right initial condition at time 0, it should be a delta function in x times the susceptibility QKQI. So that is true, of course, in the sense of large space and large time. So you imagine actually that this is kind of an average over a large space and all that stuff. So this is at hydrodynamic scale. Okay, but for now it's sufficient. Okay? So at hydro scale, this is the answer. It's very simple, powerful answer, right? So 2-point function goes along certain velocities, spectrum of A. This is where you have correlation. It's just true large scales and all that, but this is sufficient for what we want to calculate. Now, what about the current? Well, the current J0, let's say 0t, okay, well, yeah, J0, say xt qi 0, connected. The current itself, well, now I can use hydro projection. I know that AB is the same thing as projecting A over Q and B over Q and then QQ, right? So this is A0 K Q K X T Q I 0 0 0 0. See, sum over K, right? Everything is sum over K. So that's the projection idea. Now I know what this is. So this is A delta function of X minus A T C. This out matrices, and this is 0I. Okay, that's the 2-point function. J. So at the hydro scale, this is the exact 2-point function. Now, since I have the exact 2-point function, I can put it in here and just do the time integral. I told you it's a bit naive calculation, right? But it's okay. I do the time integral, so I write explicitly. This is integration of that. So there's A delta function X minus AT. What is that? X equals 0 here. 0 minus AT is fine. QI 0 0. Yes, delta function X minus AT, sorry. C 0I in the state lambda. Okay, everything you write in the state lambda. Okay. And now I do the integral. I know how to integrate the delta function. The integral kills the delta function, or the function kills the integral. There's a 1 over absolute value of A. You have to imagine you do, you do diagonalize A, and then you 1 over absolute value of the eigenvalues. So the integral is done, and you get just A over absolute value of A, which is the sine of A, and times C. And this is 0I. That's it. So this is sine of the matrix A, the C matrix, and this is 0I. Yes, and now you want to compare with that. So you conclude out of this that d beta j d lambda is equal to this minus sine of matrix A, and this is 0j. That's it. That's the flow equation. So you solve that. A depends on lambda, of course. It depends on the state. Okay? It depends on beta of lambda. So. And you solve that. Once you have the betas, you put it in here. You can write your f of lambda there explicitly as integrations from 0 to lambda d mu of the average current, beta of mu state. And then you have the answer for the full quantic set for the CGF. So okay, so that's the derivation. Now, if you do the example of CFT, where A is a 2x2 matrix, it's 0, 1, 1, 0, how this works and gives that. So it gives just that simple shift. It's not the right thing. But it is more general. So that supposedly is for, you see every many-body system. Okay, I mean, it's at hydro level, so, quantum more classical. And, so, the derivation can be done more correctly using the Fourier transforms and, taking care of the details, of being at hydro scale, but it's the same thing. And you have the answer. So it reproduces the CFT. It can be written in integrable systems because you know the A matrix in integrable system explicitly. You compare with numerics, and then it gives the right cumulants. You can check the cumulants up to C4 numerically is the right numbers in some simple integrable system models. And in principle, it's really just the general solution for this fluctuation function. Done. That's it. Am I over, or is it? I'm over a lot. Is that the case? Oh, I'm really sorry about it. Somehow I thought I had another. It's completely. I was shifted by a half hour. Sorry about this. I've abused your time there. I'm sorry. Okay. So yeah. Essentially, that's what I wanted to say. So that's it. Yes, I completely miscalculated the time. Actually, I was thinking it was. So maybe the last thing to say was that you see if A, so it's the sign of A. So if the eigenvalues of A change sign from plus to minus somewhere, then this is ill-defined. And then the calculation fails. And then the two-point function in time diverge. And then you have a dynamical phase transition where your free energy f of lambda suddenly becomes infinite. So you can see dynamical phase transition as being when your lambda, your beta of lambda state is such that you have velocity 0 in your hydro modes. This is the expansion of phase transitions, dynamical phase transitions. Thank you for your attention.